Hello and welcome. At the end of chapter 1, we looked at multiple transaction cash flow streams where money is invested at different time periods and return on the investment could also take place at different time periods. In this chapter, we are going to look at annuities. Now, an annuity is where a sequence of equal regular payments are made over time. And we have two types of annuities. We have a simple annuity and we have a complex annuity. We will come to the definition of these annuities when we look at them in more detail. So to get started, we will just first look at the basic concepts and notation that we will use for annuities. Okay, so we say that an annuity is a sequence of equal regular payments made over time. Again, we have a present value. In the case of a loan, the present value of an annuity is a lump sum of money secured, which requires a series of regular equal payments in the future. So if you, for example, take out a home loan, then you have to pay back this home loan with equal regular payments. We call that your monthly mortgage bond repayments. Now, the present value of the annuity is the lump sum of money secured one period before the first payment is made. So again, in the case of a home loan, that is the amount of money that you borrow to buy the house. And it's important to see that the first payment is made one payment period after the lump sum is secured. Now, the payments to be made must be equal and the intervals between the payments must be the same. Then payments, which we will abbreviate with PT, the payment is the fixed amount of money deposited at each payment period during the annuity. The number of payments, K, is the number of equal regular payments made throughout the life of an annuity. So if you look at the timeline on this slide, we have our present value, the lump sum of money secured in the beginning. Then the first payment is made one payment period after this lump sum is secured. And the last payment is made here at time T5. So we have 5 payments and therefore the number of payments will be equal to 5. My K is equal to 5. The future value of an annuity is the amount of money that has accumulated in an account after a series of regular equal payments have been made. So the future value is the accumulated amount when the last payment is made. So when the last payment is made, then we have our future value. For example, if you pay money into a retirement fund, let's say you make monthly contributions to a retirement fund, then the future value will be the amount that this retirement fund has accumulated to. The interest rate, IM, is the rate of interest of an annuity. So the rate of interest of an annuity is the interest rate offered or secured for the annuity. And then the payment period, the time interval between the equal regular payments is the payment period. So if you make regular payments on a monthly basis, then your payment period will be a month. If you make regular annual payments, then your payment period will be a year. We are first going to look at simple annuities. Now, a simple annuity is an annuity where the payment period and the interest rate compounding period are the same. Now, you can imagine then that a complex annuity will then be an annuity where the payment period and the compounding periods are not the same. But we start with a simple annuity. Now, to illustrate the whole idea of an annuity, we will start with an example. Example 24. Determine the present value of a loan that is repaid by 5 monthly payments of 1,000 rands each when the interest rate is 18% per annum compounded monthly. Okay, so if we draw a timeline, so this will be time T0, and we have 5 equal payments, so T1, this is the present value, that is what we would like to calculate, and we are making payments of 1,000 rands each. So equal regular payments. Equal, they're all 1,000 rands, regular, because they are made every month. And we would like to know what is the value of this present value. Okay, so the way in which we will do that is we will move each of these payments, we will move them to time T0. So first of all, if I move the first payment to time T0, then let me call that the present value for the first payment, PV1. That will then be the 1,000 rands. My interest rate is 18% per annum compounded monthly. So that is 0.18 divided by 12. And I move it back one time period or 1 month, and therefore it is to the -1. And if you calculate that, you get the following. Okay, and then we do the same for the second payment. So the second payment, or the present value of the second payment, is my 1,000 rands. Okay, I'm just going to use here 0.015. That is my 18% divided by my 12 months. I move it back 2 time periods, so that is why it is to the -2. And that gives me 970 rands. And I can do it for the third payment. And the last payment, I move it back 5 time periods, so that is why it is to the -5. Okay, so then the value of my loan, or the present value here, would just be when I add all the present values for the 5 payments. So that would be if I add these amounts, and you can go and add them all, and if you add them all up, you get a value of 4,782 rands. Okay, so that is the present value for this loan. Now this is a very tedious way of solving a problem like this. We had only 5 payments. You can imagine that if you have several payments, 10 or 20 or 30 or 60 payments, that to do these calculations will be very tedious, and it would be very helpful if we had a formula to find the present value. So what I would like to show you next is how we are going to make use of a geometric series to find a formula for the present value of an annuity. Now this is, you won't really be evaluated on this formulae, but I think it is very useful to understand where the formula for the present value of an annuity come from. So on the next page, I'm just going to revise a geometric series with you. So if you have a series A plus AR plus AR squared, and so forth, we call this a geometric series. So we start out with A, and then we multiply each consecutive term with the factor R. Now, if you take the sum of the first, if you take the sum of the first n terms in a geometric series, we can find a formula for that sum. So let's just write it as the sum of the first n terms in a geometric series. The sum of the first n terms in this geometric series will be where k goes from 1 to n, and my general term will be AR to the k minus 1. For example, if k is 1, then my first term will be AR to the k minus 1, so AR to the 0, which is just A. My second term, where k is 2, will be AR to the 2 minus 1, so AR to the power 1. My third term, where k is 3, will be AR to the power 3 minus 1, or just AR squared, which is my third term. Now, the sum of the first n terms in a geometric series is given as A 1 minus R to the n over 1 minus R. Now, if you look at what we had in our example, we had, for our first term, we had the payment 1 plus our interest rate to the minus 1. That was our first term. So we can say that this is equal to A. Then our second term was payment 1 plus IM to the minus 2. So what did we, so let me just write this as AR. My second term was payment 1 plus my interest rate to the minus 2. So what did I multiply the first term with to get to the second term? I multiplied my first term with 1 plus IM to the minus 1. So from this we have that A, in an annuity, my A is payment 1 plus IM to the minus 1, and my R is 1 plus IM to the minus 1. So now we can substitute it into this formula. So if I do that substitution, my A is payment. Okay, 1 plus IM to the minus 1 is the same as just dividing it by 1 plus IM. So that is the A. Then it is 1 minus R to the N. Now my R is 1 plus IM to the minus 1. So it is 1 plus IM to the minus 1. And then I take that to the power N. And then I divide it by 1 minus R. So 1 minus, and R is 1 plus IM to the minus 1, or I can write it as 1 over 1 plus IM. Okay, and now we can simplify this a little bit further. I hope that I will fit it in here. 1 plus IM. 1 minus 1 plus IM to the minus N to the power, 1 plus IM to the minus 1, everything to the power N can be written as 1 plus IM to the minus N divided by, and now I write this 1 minus 1 over 1 plus IM, I write them on the same denominator, so that will be 1 plus IM minus 1, everything on 1 plus IM. Okay, and this, let me just do it in a different color. This one and this one will cancel out. 1 plus IM and 1 plus IM will cancel out. So I end up with I hope you can see what I have here. And this is then the formula for the present value of an annuity. The payment, 1 minus 1 plus IM, everything to the minus n, over IM. So that is then what you have on this slide. So this is a very important formula. You can add it to your list of formulas. It's also on your formula sheet. So the general solution for the present value of an annuity with K payments is payment 1 minus 1 plus IM to the minus K over IM. We know what the payment is. That is the regular equal payments. The IM is our interest rate and K is the number of payments that we make. So we can now redo our example. We can now redo example 24 by making use of this general formula. So that is example 25 in your notes, and we can just do the substitution now in this general formula. So we made payments, 5 payments of 1,000 rands each. Our interest rate was 18% per annum compounded monthly. So our effective monthly interest rate was 0.015. We made 5 payments, so my K is 5, so that will be to the minus 5. And then I divided by IM 0.015. And if you do that calculation, you get an answer of 4,782 rands and 64 cents. And you will see, and that is to be expected, that this present value is less than the 5 payments, and that is because of the influence of interest. So you can't just take 5 times the 1,000 rands. You have to take into account the influence of the interest.